Welcome back to Modern Algebra. We've come to the last theorem we're going to do about groups, and it's one of the very best theorems in the subject, in my opinion. It's called Cayley's representation theorem for groups. And before I state the theorem, I just want to remind you of a group we've looked at, sim of x, for any set x, sim of x was the set of all permutations of x, one-to-one onto functions from x to x. And we've seen that this is the symmetric group on the set x, and we've seen that this is a group under the operation of function composition. I claimed when we did it, it was the most important group, and this theorem will sort of reveal why I said that. One other thing to remind you, Sn was our abbreviation for the symmetric group on the particular set 1 through n, which is the one we looked at the most. That was a non-commutative group for most n, anyway, of size n factorial. Now, on to this theorem. So this theorem, Cayley's theorem, has two parts. We'll focus on part A for the most part in this video. And part A says that any group, G star, any abstract group, satisfying the group axioms, is actually isomorphic to a subgroup of one of these symmetric groups. In fact, it's a subgroup of sim of G. The set G, the set of group elements, is going to be the set that we use over here. G could be infinite, by the way, and this still works. Completely arbitrary group. On the other hand, part B, if it's a finite group, I will say that every n-element group G so n less than infinity, is isomorphic to a subgroup of Sn. And so, without going into the details of which symmetric group it is, it's saying that every group you will ever see is, except for the names of the elements, except for an isomorphism, is basically a subgroup of one of these symmetric groups. And this totally justifies a detailed study of symmetric groups. If you understand more properties of symmetric groups and permutations and function composition, you're secretly also learning about all groups. Every abstract group is because they all appear as subgroups of these symmetric groups. So it's a fantastic result for sort of making the abstract idea of a group more concrete. So abstract groups can all be represented, as you would say, to get this word in there, represented as much more concrete groups of permutations. Things you can actually see, you have cycle notation, you have function composition, you know exactly what it is. And there's a whole subject called representation theory, although usually for that subject, instead of using symmetric groups, you try to represent groups using groups of matrices, and we won't really talk about that right now anyway. All right, so we'll get to the proof, but the proof is going to actually use a new ingredient that we haven't really seen before. a very interesting idea that leads us to this proof, which is the idea of a left multiplication map. Which I will define right now. So the idea is that, okay, so we have this group, we don't know anything about it. How am I going to get so what's sim of g? It's functions from g to g that are invertible. How am I going to get such a function out of the group elements? And this idea will let us do that. So for any group g star in multiplicative notation, and any x, little x, in G, I will define left multiplication by x. That's going to be a function. I'll call it L sub x. L for left. L sub x, it's going to be a function with domain and codomain G. Inputs and outputs are coming from the group G. And how is this function defined? By definition, Lx applied to input little g produces output x star g for all g and g. By closure, that output is in the codomain, and by definition of a binary operation, every input produces exactly one output because x is fixed, and so when g comes in, exactly one thing, x star g, comes out as the output. So this is a valid function, and we're actually going to have to show various facts about these things. So facts about the Lx functions, these left multiplication maps. Well, why is it called that? Because we're taking the input and we're multiplying on the left by the x. So let's fix the group G, and let's fix x and y in G. The first thing, I've said it's a function, but it's actually ended up being in sim of g, so it's going to be an invertible function. And to see that, we should let's check that it's one-to-one and onto. So I claim, first of all, that this Lx is a one-to-one function. And let's prove these things. So what does one-to-one mean in this case? It means that if you give me two elements of G for all maybe C, D in G, if you do the function, if you do Lx of C and Lx of D and they're equal, the outputs are equal, then it better be the case that the inputs are equal. That's the definition of one-to-one written out in this for the case of this particular function. All right, so let's prove that. So let's fix an arbitrary CD. Let's crank through the proof templates here. CD in G. For the if statement, let's assume Lx of C is equal to Lx of D. And giving a direct proof. And then let's try to prove that C equals D. Well, what did we assume? Using the formula, we have a formula for Lx. We assumed, namely, that x star C is equal to x star D. And, well, we have a theorem about that from a long time ago. Remember the left cancellation law? We can cancel the x. And we get C equals D. So in fact, saying this is one-to-one is exactly the same statement as the left cancellation law, but in a slightly more abstract way, because we're referring to the function now, the Lx function. All right, now, okay, so done with that. Let's try to check that L sub x is an onto function, which means let's write out what that means. So we have to prove that for every maybe B in the codomain in G, there exists an A in the domain such that Lx of A is equal to B. Every output in the codomain really does occur as a function value. Okay? Well, so fix B. X was already fixed earlier. And so what we need to find an A in G. Keeping in mind the formula, we have to find an A such that X star A is equal to B. And this is actually unique solvability, although the letters names have been reversed maybe. A is the thing we have to pick here. X is fixed. But we can just see. What are we going to pick for A? Where X and B are fixed and we have to pick A. Well, try X inverse star B, which is in G. And just to check that it works, if you stick that into the Lx function, I'll skip all the detailed justifications, which we've seen many times before. So ... you associate inverses, identity, and of course it's going to end up being B in the end. You could also quote the unique solvability theorem from a long time ago to get there immediately. This basically just reproved that. All right, so it's on to. And so the main reason I wanted that is to say that, well, this function is actually in the group. Sim of G. It's not just a function from G to G, it's an invertible function. That's the definition of sim of G. Okay. And we know by theorem that the function is invertible if and only if it's one-to-one and onto. So that's just immediate from what we just did. Since Lx is one-to-one and onto, Lx is invertible. It's an invertible function from G to G. And that's what it means to belong to this group. All right. All right, one more fact before we actually get to the proof of everything. And this is the most interesting fact, maybe, which is that, I guess I've already fixed the x and the y. For any x and y, what happens if you do Lx and compose it with Ly? The composition of two left multiplication maps. I claim, as fact 4, that that's the left multiplication by x star y for any x, y, and g. Now, how do we prove this? We have to prove it. How do you show two functions are equal? Let's remember that. To show two functions from G to G, which these are, because everything's got domain and codomain G here, we have to show that they agree, so that the outputs agree for all inputs little g in G. That's the definition of function equality. We talked about that a long time ago. There's a video you can review if you need to. Okay, but that's how you do it. So let's fix an arbitrary input, g, little g, and then see what we can get. When we do the left side, Lx circle Ly, that function applied to little g, well, that's going to be L sub x of L sub y of g by definition of function composition. And what's L sub y of g? That's y star g by definition of L sub y. And then L sub x is going to take that expression and multiply on the left by x. That's the definition of L sub x. All right, and now comes the crucial step, the associative law in G, the associative axiom. Lets me move the parentheses. So I get quantity x star y star g. And what's that? That's nothing other than taking g and multiplying on the left by the quantity x star y, which is by closure is an element of G. And that's it. The function here applied to G was equal to a bunch of stuff, which is ultimately equal to this other function here applied to G for any arbitrary G in the domain. So they're equal. All right. Let's pause and erase stuff, and then we'll move into the proof of Cayley's theorem. All right, so just to recap what we just did, I'll put that over here. We have these left multiplication maps now, Lx, one for every x in G. Lx of G is x star G. We've proved that these maps are in sim of G, they're one-to-one and onto. We've proved this formula. So now we can prove part A of this theorem. Proof of A. So fix the group G star. And I'll define a function, let's call it little f. If it's going to be isomorphic to a subgroup, maybe we should start with a function that goes from G to sim of G. And what's this function going to do? If you give me an input, little x in G, let's send that to the output L sub x, which is a certain object in sim of G. So we did prove that Lx is in the codomain. And for every x, there's exactly one such function. So we have a well-defined function f. F is very strange, though. The input to f is a group element. The output to f is another function, namely a left multiplication function, a particular element of sim of G. And that might be a little bit confusing the first time you see it, but it's allowed. And this is exactly what we need for this proof. And we're gonna check several things. So let's check first that f is a group homomorphism. In other words, for all x, y, and g, we have to check that f of x star y is f of x, and remember in sim of G the operation is function composition. F of x and f of y are functions, and we compose them, and do we get this other guy? That's going to end up basically being this fact. So let's see that. Let's fix the arbitrary x, y, and g. And by using the definition of f to get rid of all the f's, what do we have to prove here? We have to prove that L of x star y, which is this guy, is supposed to be L sub x circle L sub y, which is this guy. And we did that. That's the fact over there. I think it was fact 4, or what is this fact I just wrote on the board over here. All right, so the left multiplication maps correspond as shown. So we have a homomorphism. Now, it's probably not an isomorphism, but actually, I'm now going to claim that this function here is one-to-one. Here's one of the parts that gets tricky. It's like, didn't we do that? Wasn't that fact 1 or fact 2 or something that L sub x was one-to-one? Yes, it was. We proved that these guys were one-to-one, but the L sub x's are not the same as the function f. So there's something we have to do here. And let's write out the definition of one-to-one, keeping in mind this guy right here. F goes from g to sim of g. So what we have to do is prove for any two inputs x and y in G, the domain of f, if f of x is equal to f of y, then it better be true that x is equal to y. And we did not prove that before. We proved a similar statement about Lx. Now we're going to prove the statement for f. And let's see how that works. Let's fix the x and y in G. So let's assume f of x is equal to f of y. Just cranking out proof structure here. And let's prove that x equals y. That's how you would prove this statement. And what did we assume? We assumed, by definition of f, that the function L sub x is equal to the function L sub y. And now we have to somehow prove that x is equal to y. And here too there's a sort of a subtlety, like you're not really used to function inequalities. We proved function inequalities a little while ago. Now we've assumed it. We have this as an assumption, and think what we can do. What would happen if we took this assumed equality and took both functions, these equal functions, and applied them to E, the identity of G, the identity element? Well, that's in the domain of these functions, which go from G to G. So if they're equal functions, it must be the case that applying them to one particular input gives me the same output. It's true for every G in G. Every input, in particular for this input. All right, so that's something we can do. But now that I've applied the functions to an input, I can use the formula. So that means that x star E is equal to y star E, because that's what Lx of E and Ly of E are. And E is the identity, so x star E is equal to x. And y star E is equal to y. So we get that x is equal to y. All right, and maybe there's somewhere I should draw like a picture or something to help you have intuition here. So you've got G and sim of G, and we've just shown G probably has lots of elements, right? X, Y, and so on. But what we've just finished showing is that if you have two different elements over there, x and y, that are not the same input, then the Lx function over here and the Ly function are different over in the codomain. And of course, all these other group elements are mapping to their own left multiplication maps. But what almost always happens is that there's going to be a ton of other stuff in sim of G that are not in this image here. So this is like a picture of the f that we just created. And here's the image of f. So there's one last little thing we have to do. Let's give that a name. Let's call this M, I guess. We know by general theorems f is a group homomorphism, right? We proved that. So we can conclude that M is a subgroup of sim of G. Likely not the entire thing. Sim of G is probably much bigger than G, at least in the finite case. And even in the infinite case, it's probably not, this map is probably not onto. But it doesn't have to be, because now we can just sort of adjust the f, which is one-to-one. So by shrinking the codomain of F from sim G, the original codomain, down to the actual stuff that got hit, this M, which is a subgroup, by the way, we get a group isomorphism. You could call it F1 or something, from G to M. And the formula for F doesn't change, the inputs doesn't change, the fact that it's homomorphism, that it's the same formula. F1 of X is L sub X, just like before. The only thing that's changed is our advanced notice of what the codomain is. Now the codomain is defined to be M, which is exactly the set of stuff that comes out of F and F1, so that basically forces it to be 1-to-1 and onto. And it was onto. It was already 1-to-1. It was already a group homomorphism, so it's a group isomorphism. And so that gives us the thing we want, that the group G is isomorphic to M, where M is a subgroup of sim of G. And that finishes proving part A of Cayley's theorem. I actually won't give a full proof of part B, but what I want to do is we'll do some examples of the proof that we just did, which will make it much more concrete, I hope. And after those examples, I'll just say a few words about how you prove B. All right, so for the examples will clarify the proof, hopefully, but also show you just how explicit everything is. It's not some unknown subgroup that you can't possibly figure out what it is. If you give me the group and you know the group multiplication table, you can figure out exactly which subgroup of sim of G you're going to look at. So let's look at the integers mod 4, which is the set 0, 1, 2, 3, with a group operation. Okay, so it's addition mod 4, not multiplication. All right, so left multiplication, you would call it a left addition map. But the way we're going to get this isomorphism, let's just go ahead and recreate this table one last time, the addition table, mod 4. And by now you're used to the cycling of the rows that lets you quickly create the table. Each row is a cyclic shift of the one above it. Okay, and let's take a look. I claim that once you've got this table, so first of all, let's write so what's Lx of G? If star is circle plus, then what we're actually adding x plus G mod 4. For any two elements of Z mod 4. So a left addition map. Sometimes it would be called more, in a neutral word, it could be called a left translation by X. You'll also hear that phrase. Or left addition, whatever, in the case of an additive group. But we can see what these things are. We can figure out specifically L0, L1, L2, and L3 in an especially easy way if we do the two-line form, because look at 0, for instance. To get the outputs for 0, 1, 2, 3, I have to take 0 plus 0, 0 plus 1, 0 plus 2, 0 plus 3, which is exactly this row of the table. So by just copying the row, essentially, I get the output in two-line form for the appropriate L map. Same with 1. If I want to add 1 on the left to everything in G, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 0. And I just copy that row down. So the inputs are always 0, 1, 2, 3, whatever order you want to list them in. But the outputs are just copying the rows of the table. By the way, it's sometimes called the Cayley table for the group, in honor of Cayley, who came up with some version of this theorem early in the days of group theory. right, and again, it's just so easy if you're lucky enough to have the table in front of you to write these maps down in two-line form. And Sudoku Theorem is another way of saying that these are permutations. Every row has every group element exactly once. That's another way of thinking about why L sub x is always 1 to 1 and onto. And the fact that the function f is onto is saying that the things that came out, these are 4 different functions coming out from the 4 different group elements. Okay, and we could write them in cycle notation if you wanted to. Like this first one is the identity map on the set Z mod 4. L0 is, and that's always true, by the way, because group homomorphisms preserve identity. This is the ID. The identity function could also be thought of as the E of the symmetric group on Z mod 4. Okay. Meanwhile, L1 in cycle notation is the 4 cycle 0, 1, 2, 3. So I'm writing cycle notation now. Although the two-line form is easier for purposes of the theorem, but just for our benefit, have L2, we see that we get a 2 cycle 0, 2 times the other 2 cycle 1, 3. And over here, L3, left addition by 3, ends up being the 4 cycle 0, 3, 2, 1. And then you can check if you made the multiplication table for these guys, you discover, I mean, it would basically be the same table, but with L everywhere under function composition. Thanks to this fact, without even calculating any of it, the theorem we already checked says it's gotta work like this. I just put, everywhere I saw a number, I put L sub that number. And this is the group M, the image of that from the proof. So in other words, to summarize, Z4, the integers mod 4 under addition mod 4, is isomorphic to the particular subgroup of this symmetric group consisting of these 4 elements. The identity, 0, 1, 2, 3, 0, 2, 1, 3, and 0, 3, 2, 1, which is a 4-element subgroup of sim of 0, 1, 2, 3, as promised by the theorem. Now I'm going to just say one little thing about part B, which is that part B that I didn't prove yet says that every 4-element group in particular is isomorphic to a subgroup of S4. This is not S4, because the symbols being permuted are 0, 1, 2, 3. But in fact, and hopefully this is highly believable with this example in front of us, sim of 0, 1, 2, 3 ends up being isomorphic to this sim of 1, 2, 3, 4, which is S4, because you could basically just add 1 to everything. Instead of calling them 0 through 3, you could call the symbols 1 through 4, and you would get that Z mod 4 is also isomorphic to a subgroup of S4. Just relabel all the individual symbols that are being moved, but keep everything else, like the cycles and so on, are just the same as they were before. And the claim that's slightly tricky to prove in general is, here it was pretty, the symbols were so similar, you just add 1 to everything. But no matter what the symbols in the set are, the claim is that if G is an n-element set, in this part B here, for any n-element set, G, sim of G ends up being isomorphic to Sn. And I'll write that down again at the very end after our second example. But that's the only new ingredient you need to get part B, is this idea of relabeling at the very end to use the standard symbols 1, 2, 3 up through n, instead of your group G, which could be like G1 through Gn. All right. So, example 2. So I'll give you an abstract group via its table, G star, where the set of elements is A, B, C, D, lowercase letters A, B, C, D. And I think we've seen this one before as well, in some form. It's actually secretly Z2 cross Z2. I'm deliberately using kind of neutral letters here. All right, and we're just told it's a group. That's not completely obvious from the table because of associativity, but it is a group. And what we'll do is we'll find the subgroup of sim of G isomorphic to G by following the proof of the theorem. And we'll do exactly what we did before, just basically reading off the rows of the table to get our left multiplication map outputs. So for instance, A is the identity here. Left multiplication by A sends A, B, C, D to A times A, A times B, A times C, A times D, which is A, B, C, D. Left multiplication by B, on the other hand, sends A, B, C, D respectively to B, A, D, C. Left multiplication by C gives me C, D, A, B as the outputs. And finally, left multiplication by D gives me D, C, B, A. All in two-line form. And so G is going to be basically isomorphic to this set of LA, LB, LC, LD, which is a subgroup of sim of A, B, C, D. Permutations of those 4 letters. Again, cycle notation might be revealing, although not as straightforward as the two-line form, but it's still neat. These are all 1 cycles. We discover that LB flips A and B, flips C and D. LC, on the other hand, flips AC and flips B and D. So 2 cycles. And here we get AD, BC. It's actually not an accident that we get this sort of 2 copies of 2 cycles every time, although we won't prove that. But anyway, and we've also, I think in a homework, we've seen some version of this before. And I just again want to make the point, well, that's a subgroup of sim of A, B, C, D, but how are we going to get a subgroup of S4? So to get G isomorphic to some subgroup of S4, well, we can just rename everything. The elements, I mean. We could say A is 1, B is 2, C is 3, D is 4. And then, just using cycle notation for convenience, the H we therefore get that's isomorphic to this 4-element group is the identity on the symbols 1 through 4. And then we get a bunch of products of 2 cycles. 1, 2, 3, 4. This one is 1, 3, 2, 4. And this one is 1, 4, 2, 3, I believe. And that's a subgroup of S4. And okay, so that's all I'll specifically say about the proof getting yourself to Sn as opposed to sim of G, except just to remark in general, if G is little g1 through little gn, is any n-element set, doesn't even have to be a group, just a set of n things, then can check that sim of G is isomorphic to Sn by, and this is the part that's slightly imprecise, by renaming G1 to B1 and so on. And if you're not quite sure about the precise details of that, I'll make like a review problem or something that guides you through in somewhat more detail exactly how you can construct an isomorphism here by doing this. Here we just did it informally in the context of an example, but it's absolutely a general fact. All right? So we'll say we kind of proved B, and that basically brings us to the end of the group theory we're going to do in this course. We've now had a taste of what you could call permutation representations of abstract groups. I might just mention one last little thing, which is that can also show Sn is isomorphic to a subgroup of matrices, of GLN of R, n by n invertible matrices. And therefore, by using this, every n-element group, G, is isomorphic to some matrix group, namely some subgroup of GLN of R. I basically taken the subgroup you get from here and going through this isomorphism to change everything into a matrix. And so this leads us into this huge subject called matrix representation theory, where you start with an abstract group and try to find groups of matrices that reflect the structure of G. It could be here an isomorphism. There's also homomorphisms into matrix groups. And that's just a huge subject in itself that sort of combines group theory and linear algebra. The permutation representation sort of connects group theory to combinatorics. So there's all kinds of interesting directions we can go. And much as I'd like to go there, we only have so much time in the introductory course, so we're going to cut this video right here. It's the end of groups. And next time we'll move on, finally, to rings and fields. See you later.